Unit 3 Review. The purpose of this video is to review the topics from Unit 3. Unit 3 focused on axially loaded members. I will review stress, deflection, constrained deflection of statically indeterminate members, and constrained thermal deflection. Use the times shown to jump to a specific topic. Axially loaded members are structural members where the primary loading occurs along the primary axis of the member. These members are typically long and slender, like columns in a building, members in a truss, or links in a machine. These members are sometimes called two-force members and take tension or compression loads. The stress in an axially loaded member is normal stress, and is computed as the internal normal force divided by the cross-sectional area, with the area taken perpendicular to the member axis. When an axially loaded member is loaded in tension, it gets longer. When loaded in compression, it gets shorter. The change in length, or deflection, is computed as the internal normal force times the length divided by the material modulus of elasticity and cross-sectional area. The deflection formula is derived by combining the normal stress, normal strain, and Hooke's law equations, and solving for the change in length, delta. A more general form of the equation is shown as deflection is equal to the sum of PL over EA. This form is useful when there's an abrupt change in the internal load, material property E, or cross-sectional area. We apply the equation by dividing up the member into segments of equal P, E, and A. Find the deflection for each segment, and sum them up to get a net deflection for the full member. Another general form of the deflection equation is deflection is equal to the integral from 0 to L of P times dx over E and A, where P, E, and A can be functions of x. This form of the equation is useful when there are gradual changes in the internal force, area, or material properties over a length of the member. I will now review two scenarios where the general forms of the deflection equation are useful. In the member on the left, two concentrated axial forces are applied. Since the deflection equation is based on internal force, it can be very helpful to plot an internal force diagram. Here's the diagram for the member on the left. Note that tension forces are plotted as positive. For the left section of the member, the internal force is equal to P1. For the right section of the member, the internal force is equal to P1 minus P2. Here it is negative since P2 is greater than P1. The jump to 0 at the right end of the graph is equal to the reaction force at the support. If the cross-section and material property E are constant, then this form of the deflection equation can be used. The numerator of the equation can be written as the sum of the area under the internal axial force diagram plot, being careful to take sign into account. In the member on the right, a uniformly distributed axial compression load is applied along the full length of the member. A plot of the internal axial force would look like this. The magnitude of the internal force gradually increases as we move from left to right, and is at a maximum at the support, where all the external load is accumulated. Note that the slope of the internal axial force diagram is the applied distributed load. It's negative here since it is a compression load. If the cross-sectional area and modulus of elasticity are constant, then this equation may be used. The numerator of the equation is equal to the area under the axial force diagram. In this case, the area is a triangle. The sum of P times L is the area of the triangle, 1/2 times the base dimension, L1, times the height, negative WL1. Divide the sum of P times L by EA to get deflection. The formula with the integral could also be used to get the same result. P is a function of x, and here is equal to negative w times x. Integrating would give us the same result as before. So here's an axially loaded member that has a point load applied at A, and then a distributed load applied from B to C. And we're given the cross-sectional area and the modulus of elasticity. And we want to find the deflection at point A from these loads. So at A we have a point load, that's pulling A, so at least from A to B it's going to be feeling tension. And then between B and C, that distributed load is acting in the opposite direction, so that's going to be undoing some of that tension load and possibly causing some compression. So the first thing I like to do is plot an internal force diagram. I've got my coordinate system set up here, and I see at point A that we're going to jump up because of that 12,000 pound force. We're going to jump up because it's causing tension. Jump up to 12,000. Then from A to B nothing's going on, so it's going to be constant from A to B. Then from B to C we have our uniformly distributed axial force being applied. And it's being applied at a rate of 500 pounds per inch. So for every inch there's 500 pounds being applied. And since that's going in the opposite direction of the 12,000, that's going to make this our graph then start to go downward. And since it's distributed, it'll be a linear function. So for every inch I'm going to drop 500 pounds. So if I go over 42 inches, I'm going to drop by 21,000 pounds. So I'll end up at a negative 9,000 by the time I get to at the time I get to point C. And I will jump back up because I have a load at point C, a reaction force at point C that must be pointing to the right. So now I have a plot of my internal force diagram. I know the length from A to B is 24 inches, but I would like to know where I cross from positive internal axial force to negative. At point B, at the start, I'm at 12,000 pounds, and then I'm going to go down at a slope of negative 500 x, and so I can solve for x, the x which makes this equation equal to 0, and I find that x is 24 inches. So I'm going to be at 0 internal force at 24 inches to the right of B, and that means it's an additional 18 inches from that point to point C. Now there's a couple of ways I can solve this. One method is to use the integral form. And here's the general form of that equation. Now if we look at our diagram, our internal force diagram, we see that there's actually two sections. From A to B we've got a constant force, internal force, and then from B to C we have this linear function that we would need to define to integrate. So I'd have to break this integral up into two integrals. Okay, so here's the deflection in integral form. I've broken it into two. From A to B, we have a constant load, and since we also have a constant area and constant E, I've just pulled E and A out of the equation, and I guess technically I could even pull the P 12,000 out. And but anyway, that's a constant. From B to C, then we also have a constant EA, so I pulled that out of the integral, and now I have P defined as a function of x, and I'm going to say that right point B is our new starting point origin 0. So from B to C that's going to be 42 inches, so I'm going to integrate from 0 to 42, and the equation for my internal force then is a linear function. I'm going to start at 12,000 at x equals 0, and as I move to the right I have a negative slope of negative 500 times x. And I can check this equation makes sense. When x is equal to 0, I'm at 12,000 positive. When x is at 42, I'm at negative 9,000, so that equation works. Okay, so I've evaluated my integrals, and this is what I get. I've got the left side of B and the right side of B. And now I can go ahead and calculate deflection by putting in values for E and A. We were given the E is 14,000 KSI. So let's see, let's think about units here. This value is P of X times dx, and P is in the internal force, so that's in pounds, and the dx, that's just the length. The length is split up into a bunch of dx's. That's in inches, so the units in the numerator are inch pounds. So for E, which is 14,000 KSI, I want that in PSI, so I'll say 14 million PSI, and our area we were given as 3.5 inches squared. And everything cancels out except for inches. And I calculate that we get a very small deflection, 0.0072 inches. And it came out positive, so that means point A is actually moving to the left. This bar does get a longer, net a little bit longer. That's what the positive sign means. The bar gets longer. If it came out negative, that means the bar is shrinking. Now, there is a way to solve this problem without using integrals. In fact, it's faster, probably. Let me show you. We can use this form of the equation to solve the problem. E and A are constant, so I'll save those till the end, just like I did before. P times L is just the area under our curve. This is our internal force plotted as a function of length. So the area under the internal force diagram is P times L. So we can just break it up into a rectangle and two triangles. Okay, so what I've written here is that this first term is from A to B. The second term then is the triangle from B to the point where we go to 0. It's 24 inches long, 1/2 base times height. And then the last term is the last triangle. Notice that its length is 18 inches and the height is negative 9,000. Make sure you get the sign in there right. And if I evaluate everything in brackets, it comes out to be 351,000. That's the same thing we got when we integrated. The first term is the rectangle, that's the 288,000. And then the two triangles, one positive, one negative, those two areas sum to 63,000. So we're doing the same thing. When we integrate, we're just taking the area under the internal force diagram. So it's the same. And we get the same net deflection in the bar. The next topic is constrained deflection of an axially loaded member. An example is shown. The bar has fixed supports at both ends. A free body diagram of the bar looks like this. Summing forces in the y direction yields this equation, with two unknowns. There are no other useful static equilibrium equations, so this member is considered statically indeterminate. It cannot be solved with statics alone. We need another equation with the same unknowns to solve for the reactions. We can use a deflection compatibility equation. The compatibility equations describe the deflection constraints within a member and are written in terms of deflection. We considered two methods for obtaining a compatibility equation: the force method and an alternative method where we write a compatibility equation that constrains the deflections within the deflection limits available. First, let's consider the force method. In the force method, we first remove a redundant or extra support. In this case, I've removed support A. Next, we find deflection at the redundant support location from the applied load. In this case, our applied load is a point load P at point B. When it is applied, the member is going to shrink down, causing deflection delta P to occur at point A. Next, we find the deflection at the redundant support location from the force caused by the redundant support reaction. In this case, I've redrawn a free body diagram with the redundant support still removed, but in its place I have put on the reaction AX, acting to counter the force P. And I compute the deflection delta AX from that force, AX. Next, I write a compatibility equation that sets the deflection at the redundant support equal to 0. In this case, the deflection from support reaction AX and the deflection from the applied force P cancel each other out. So the sum of those two deflections is 0. Then we expand our compatibility equation by substituting in PL over EA for the two deflection values, using the corresponding loads, lengths, etc. The alternative method for finding a compatibility equation is to inspect the problem constraints and loads and determine a compatibility equation that constrains the deflections within the deflection limits available. In this case, we can imagine that when the load is applied to point B, B will deflect in the direction of the load. This means that section AB will get longer and section BC will get shorter. Since the supports cannot move, all deflections will have to take place within the length of the bar. For the deflections to be compatible, the increase in length of AB must equal the decrease in length of BC. We can write that in a compatibility equation like this. Then we substitute in the deflection formula, written uniquely for each of the two deflections. With the compatibility equation and the static equilibrium equation, we can solve for the unknown support reactions. Here's an example problem with constrained deflection. There's a bar between supports at A and D, and the bar has two cross sections, a circular cross section from A to C and a square cross section from C to D. And not only is the cross section different, but also the material properties. The modulus of elasticity in the section from A to C is 60 gigapascals, and from C to D the modulus of elasticity is 100 gigapascals. And at point B, halfway in the middle of member AC, there is a 20 kilonewton load applied to the right. And we want to find the support reactions at both A and D. We are going to need a compatibility equation to solve this, and we have two ways to get it. The first way is the force method, so let's do that. Now in the force method, I'm going to divide our original problem into two parts, and both of these parts are statically determinate. In the first part, I'm going to remove a redundant support, and I've decided to remove the redundant support at point D. And it doesn't matter which one you choose, but it turns out that'll make this problem a little bit easier to solve. With the support at D removed, now point D can deflect, and it's going to deflect to the right as the member elongates under that load. Then I'm going to draw another free body diagram and say that the sum of these two free body diagrams equals the original member. Now, in the second free body diagram, I've got to add what's missing in the first, and that is the support reaction at the support D that was removed. And it's going to be acting to the left to counter the 20 kilonewton load. I'm not going to put the 20 kilonewton load here on this free body diagram because when I add them up, then it would double to 40, and that is not the problem. Now, under the applied support reaction load, dx, that is going to cause this member to move because there's no support there. It's just a load. It's going to cause the member to deflect. It's going to move to the left at point D, some amount. I'll call it delta dx. For these two problems to add up to the original problem, then the deflections have to be equal to each other. And that is our compatibility equation. So I can write that delta P minus delta dx is equal to 0. Those two deflections cancel each other out. I can rewrite our compatibility equation like this and say the magnitude of delta P is equal to the magnitude of delta dx. And now I'm going to expand my deltas by adding the PL over EA terms. First, delta P. Delta P, if I'm looking at my free body diagram, the top one, delta P is caused by the 20 kilonewton load. And that 20 kilonewton load is only felt from point A to point B. If I was to cut anywhere between B and the ND, there I would see on the internal cut surface there is no load. It only if I cut somewhere between A and B is there axial load. So I only need to write a deflection equation for A to B. So my force P is 20 kilonewtons. The length is the length from A to B. That's 0.2 meters. E is the modulus of elasticity. That's 60 gigapascals for member AB. And the area is the area of member AC, which is 1960 millimeters squared. So yes, I do have mixed units here. That's not going to be a problem in this case. I usually don't recommend that, but in this case that's not going to be a problem because we're just setting one deflection equation equal to another, and as long as we maintain similar units, they'll just cancel out, as we will see. Now on the other side of our equal sign is delta dx. Now delta dx is caused by this force dx, which is being felt through the whole rod from D all the way back to the support at A. And since that rod changes both shape and modulus, I'm going to have to split my delta dx equation into two terms. One from A to C, and then the other from C to D. So I'll look at A to C first. It has an internal force is just going to be the force dx, which is unknown at this point. And the length is the full length of the member, so that's 0.4 meters. That's the full length of member AC. Its modulus of elasticity is 60 gigapascals, and its area is 1960 millimeters squared. And then for member CD, the internal force is the same, dx, which we don't know yet. Length is 0.5 meters. Modulus of elasticity is 100 gigapascals, and the cross-sectional area is 3,600 millimeters squared. And now we can go back to the whole units issue. Look at gigapascals is in every single term, so it cancels out. Millimeters squared is in every single term in the same spot. It cancels out. Same is true with meters. On the top, it cancels out. So we're only left with kilonewtons. So when we solve for dx, it'll be in terms of units of kilonewtons. And now if I simplify it and then solve for dx, I get that dx is 7.1 kilonewtons. And from static equilibrium, I can draw a free body diagram of the full original member. And by summing forces in the x direction, I see that ax is equal to 20 kilonewtons minus dx. And I now have my two support reactions. So that was solving this problem using the force method. Now let's resolve this problem using the alternative method for finding a compatibility equation. In the alternative method, we just inspect the problem and come up with a compatibility equation based on keeping the deflections compatible within the limitations. When we inspect the problem, we see that because of the 20 kilonewton force being applied at point B, section AB is going to get longer. And that means that section B to D must get shorter. And the amount AB gets longer must be equal to the amount that BD gets shorter. That's what we mean by the deflections have to be compatible. So I can write a compatibility equation that says the length change of delta AB, which is going to be a positive increase, minus the length change of BD is equal to 0. Or we can say that the magnitude of the two deflections, AB and B to D, are the same. Now I've drawn a quick free body diagram of the member and with the support reaction shown. And the reason I've done this is because I want to plot a diagram of the internal normal force. And we see that at point A, there's going to be intention by the amount equal to AX. So from AX to point B, the internal force is equal to whatever support reaction AX is. And then at point B, that's going to chop by 20. And at that point, it's going to stay constant all the way till D. And we can see that we're going to have to jump up by an amount dx. So this is equal to negative dx here. And this difference is 20 kilonewtons between the two. So we can see that in member AB, the internal force is AX. And in member B2, or the members from B to D, the internal force will be dx is the magnitude. So I'm going to use that information when I expand my compatibility equation. So first, I'm going to solve for delta AB. And we can see that the internal force, P, is AX from our plot. It's PL over EA. The length is the length from A to B. That's 0.2 meters. E is 60 gigapascals. That's given. And A is 1960 millimeters squared. And again, it's okay to have mixed units because they're going to cancel out here. So now let me look at delta BD, the other side of our compatibility equation. Delta BD is occurring from B to D, but along that length, the cross-section and also the material changes. That's going to be a change at point C. So I'm going to break up delta BD into two terms. One from B to C, and the other one from C to D. So in both terms, the internal force, and I'm just looking at magnitude here, the internal force is dx, so I'll put dx in both of them. The length from B to C is 0.2 meters, and from C to D is 0.5 meters. For member BC, E, the modulus of elasticity, is 60 gigapascals, and the cross-sectional area is 1960 millimeters squared. And for member C to D, the modulus of elasticity is 100 gigapascals, and the area is 3600 millimeters squared. And I've got one equation with two unknowns in it, ax and dx. That's okay. So using algebra, I can reduce the equation and then solve for ax in terms of dx. I have one more equation that I can get. That's my static equilibrium equation. I can get it from my free body diagram. Here it is. I can get it by summing forces in the x direction equal to 0. And now I can do a substitution of ax from my compatibility equation into my static equilibrium equation and solve for dx. I get 7.1 kilonewtons. And I can stick that answer back into the equation for ax and solve for ax. It's 12.90 kilonewtons. And I get the same results I did when I used the force method. Next, thermal deflection. Applying forces is one way to cause a member to deflect. Another way to cause deflections in a member is to change its temperature. The thermal deflection equation is shown. It is equal to alpha, the thermal expansion coefficient, times the change in temperature of the member, times the length of the member. Thermal deflections in members occur in all member dimensions, but in this course we are primarily concerned about axial length changes. Note that the change in length can be either positive or negative. If thermal expansion occurs in a constrained member, very large internal and reaction forces may develop. These should be considered in engineering design. Let's look at what happens. Here's a constrained member which is subjected to an increase in internal temperature. The bar wants to grow in length by the amount delta T. However, support B prevents the thermal deflection. To keep the bar the same length, a reaction force is generated at support B that causes a force deflection sufficient to counteract the thermal deflection. In constrained thermal deflection problems, there are balancing thermal deflections and force deflections. To solve these problems, we write a compatibility equation that constrains the deflections within the deflection limits available. A general-purpose compatibility equation is shown. Delta gap represents a gap that exists between the end of a member and a rigid support. If there is no gap, delta gap is taken as 0. Here's a problem that incorporates constrained thermal deflections. We have two blocks situated between rigid supports. The dimensions of the blocks are shown. Also given is the modulus of elasticity of the block material, the thermal expansion coefficient of the block material, and also the stress at which the blocks will fail in compression. There's a gap between the two blocks equal to 0.05 inches. The problem says, determine the required change in temperature of the blocks that causes them to fail in compression. Let's consider what's going to happen. As the temperature goes up, the blocks will expand, and they will close the gap and come into contact with one another. As the temperature continues to increase, the blocks will push against each other and against the rigid supports. They want to continue to grow, but they cannot because they are constrained. This will cause a compression force to develop within the blocks, and if the compression force is high enough, the blocks will fail. Let's calculate what force is required to cause a block to fail in compression. Here's the equation for the stress in a block. We can rewrite it to calculate what normal force is required to fail the block. The cross-sectional area of the block is 3 inches by 4 inches, so 12 square inches. Therefore, a force of 96 kips is required to fail a block. Now, let's write the general purpose compatibility equation for thermal deflection problems. Here's our general purpose equation. We have a gap between the two blocks, so we know what that value is. So we want to add all the deflections that are going to close the gap. Really, there's two kinds of deflections. There's thermal deflections and there's force deflections. So it'll be the thermal deflections will cause that gap to close. And we're going to have 2 of them, one for each block. Because the blocks are identical, we can just take our thermal deflection equation for one block and multiply it by 2. Now, the deflections that are going to open the gap, well, let's think about that. There's no deflection that's going to actually cause the gap to physically open once it's closed. But as the blocks are compressed, the compression force will cause them to shrink, and that's in the direction of opening the gap. So our force deflections would be the deflections that are causing the gap to open. So we're going to have a force deflection in each block, so we will calculate the deflection in one block and multiply it by 2. So I can rewrite the equation as shown. And now let's expand it. So now I'm showing we have 2 thermal deflections that are going to close the gap, 2 force deflections that are acting in the opposite direction to open the gap. Now let's just fill in values. Okay, I filled in the variables in our compatibility equation. The gap was given. Alpha is given. Delta T is what is our single unknown that we are solving for. The length of one block is 8 inches. P, the internal force, is going to be the force required to fail a block. It's 96 kips. Length is also 8 inches. E is given. And A we computed from the cross-sectional area. Now we can solve for delta T using algebra, and we get that the change in temperature required is 194 degrees Fahrenheit. This completes the review of topics from Unit 3.